We're now going to discuss the volume of a parallelepiped, and we are going to use the vectors u, v, and w in order to sketch it. So I'm going to begin by making my vector v intentionally horizontal, and then u will come back here, and this is going to be the vector that creates basically the floor of my parallelepiped. And then my vector w is going to be the one that gives me a little bit of height here, giving me that third dimension. And so we'll begin by just drawing this three-dimensional solid. I'll have a side that is essentially the front wall that is going to have an edge parallel to V and parallel to W. We're going to go parallel to U to give me some depth here, and then finish up the construction of this parallelepiped. And so now in order to determine the volume, we're going to consider the height of this three-dimensional solid, call this h, and let's actually extend this in the third dimension here, basically slicing into the parallelepiped and chopping off this little cheese wedge piece and essentially pasting it here over on the other side. Now when we do that, we can basically see that this parallelepiped is going to have the same volume as the rectangular solid if I were to chop that cheese wedge off and pull it on over to the other side and create a rectangular solid. They're going to have the same volume. And so we can really think about the volume of this 3D object as being the area of the base, which is the same thing as essentially length times width, but then multiply that through by that height quantity. And so first of all, let's talk about the area of the base. And as we remember, the area of a parallelogram that is created by two vectors is going to be the magnitude of their cross product, right? So we're going to say, let's look at the magnitude, and let's go v cross u in order to get the magnitude of the cross product of the two vectors that are generating the base of that parallelepiped. Now we're going to work on trying to find the height. So the first thing that we're going to do is we're going to consider the cross product of v and u. We already determined that the magnitude of that cross product is going to give me the area of the base, but that cross product also gives me a vector that is both perpendicular to v and perpendicular to u. So when we look at v cross u, we need to determine which direction that's going to be headed in. Am I going to be getting a vector that's going straight up and perpendicular to that base, or straight down and perpendicular to that base? So let's look at the right-hand rule here. Remember, if we are crossing v and u, we're going to take the heel of our right hand and put it along the second vector. So that's the heel of our right hand, essentially right here. The knuckles of our right hand are going to fall on the shared initial point, and the fingers of our right hand are going to go along the first vector v. And when we orient our right hand in this way, that tells us that our thumb is actually going to be pointing up, and so the v cross u vector is going to be going up. So here's our vector v cross u. Now let's consider the terminal point of our w vector. Let's take a light and shine it down onto that kind of terminal point and project a shadow vector onto the v cross u vector. So essentially what we get with this shadow vector is, we call this the projection vector. This is the projection of w onto v cross u. And notice that the magnitude of this projection vector is the same as the height of our parallelogram. So if we could determine the magnitude of this vector, we're going to actually then call that our height. Instead of calling it the magnitude of the projection vector, we could also consider this to be the value of the component of w onto v cross u. Now, this component could be a positive or a negative value. Remember, this is the signed magnitude of the projection vector, depending on the angle in between those two vectors. So in order to ensure that this scalar quantity, remember this is a scalar quantity giving me essentially the length of the vector, in order to ensure that it's positive, I'm going to wrap this in absolute value bars. Now, We need to start to be really careful here because we're going to be using vertical bars that are absolute value bars as well as vertical bars that are magnitude bars. So for this video, I'm going to use the double line magnitude bars just to overemphasize when I'm talking about the magnitude of a vector, and the single lines are going to be reserved for the absolute value of a scalar quantity, right? This is the magnitude of a vector or the abs val of a scalar quantity. Now let's recall the formula for the component of W onto V cross U, and that is going to be the V cross U vector dotted with the W vector, which is going to give me a scalar quantity in the numerator, and then we divide that by the magnitude of the V cross U vector. So again, being very careful to refer to magnitude with double line bars, and abs vals are the single line bars. So this is abs val on the outside, mag bars on the inside. So let's split this up now. I'm going to split it numerator and denominator. So the numerator is a scalar quantity. So these are going to be absolute value bars in the top that are surrounding the V cross U dot W scalar quantity. And then that's going to be divided by, these are going to still be magnitude bars, but the magnitude of a vector does give me a positive quantity, so I don't need to additionally wrap abs vals around the denominator. The only thing that could be a negative quantity in this fraction is the numerator. The dot product could give me a negative quantity, so we're just going to reserve and put those abs val bars in the top only. Now, let's go back to our volume formula, which was that we were looking at the area of the base, and then we're going to multiply that by the height of the parallelepiped. So the area of the base is the magnitude of the cross product of the two vectors that generate the floor, right? That's the area of the parallelogram, that is the floor. And we just found out that the height, which was all this stuff here, is the absolute value of V cross U dot W over the magnitude of V cross U. Now let's notice then that these magnitudes will cancel each other out, and what we're left with as the volume of the parallelepiped is going to be the absolute value of V cross U dot W, and close that out. So this is going to be the volume of the parallelepiped that can be calculated by getting the cross product vector and then dotting that with the third vector that finishes off that parallelepiped. Now, another thing that we need to make mention of is that the quantity V cross U, that vector, dot a third vector, is also called the scalar triple product. And there is a property of cross products that states that when I'm looking at V cross U and then dotting that with the third vector W, that would give me the same scalar quantity as V dot the cross product of U cross W, right? So these quantities are going to turn out to be the same. And for right now in this video, we're just going to state the property without proving it.